Well, students, in the last class, we have studied bisection method. In this lecture, we will study another closed domain method called Regula-Falsi method. Although bisection method is a very simple method to understand, both geometrically and computationally, rather it has a very slow converging nature. For instance, if the root of our nonlinear equation that we are interested in is lying very close to one of the boundary points of the interval that we have located, say if our equation f of x equal to 0 is such that the graph of the function f looks like this, then how the bisection method goes, if you recall, in the first iteration, we will be having x1 as the midpoint of a naught, b naught. And in the second iteration, we would have defined our a1 as x naught and b1 as b naught. And then we would have bisected the interval a1, b1 and obtained x1. And in the second iteration, we would have taken a2 to be, sorry, this is x2 and b2 to be equal to b1, right? So like that, we would have progressed rather slowly to the root r. Now the question is there a better way to reduce the length of the interval in such a way that we may approach to the root a bit faster than the bisection method? Well, there is another way of defining the point by which we will be dividing our interval into two parts. Instead of exactly bisecting the interval, why can't we just take the point a naught, f of a naught, which is this point, and b naught, f of b naught, which is this point, and now you draw the line joining these 2 points and take the point of intersection of this line with the x-axis as your point x1, and now you see the sign change on the either side of x1. In this case, the sign change will happen in the second part of the interval. Once you have this, now you define a1 to be x1 and b1 to be b naught, and again you consider a1 f of a1, and now this will become b1 f of b1. Again draw the line joining these 2 points and take the point of intersection of this line with the x-axis as x2. You can see that you are going a bit faster to the root than how we would have gone with the bisection method. Remember, bisection method would have taken x1 as this and x2 as this and so on, whereas your new idea is little faster in approaching the root. In this particular case, well, it may not happen always. I'll leave it to you to think, at least geometrically, when does the bisection idea approaches to the root more faster than the idea shown here. And this is the idea behind Regula-Falsi method. Let us formally derive the formula for Regula-Falsi method and devise the algorithm as we did in the bisection method. From the basic idea of the Regula-Falsi method, we can clearly see that Regula-Falsi method is a closed domain method. Therefore, the first step of the Regula-Falsi method is to locate a root of our nonlinear equation f of x equal to 0. How we will do? Well, we have to find the numbers a naught and b naught such that f of a naught into f of b naught is less than 0. And not only that, we have to choose this a naught and b naught in such a way that f is defined in the whole interval a naught b naught, and also f should be continuous. This procedure is not new to us because we have already learnt it in the bisection method. Now the question is, how are we going to define xn? In the bisection method, we have chosen xn as the midpoint of the interval an minus 1, bn minus 1, whereas here we will be defining xn as the point of intersection of the line joining the points an minus 1, f of an minus 1 and bn minus 1 and f of bn minus 1 with the x-axis, right? So how will we define the line joining these 2 points? Well, from our basic geometry knowledge, you can see that the line joining these 2 points is given by this expression. Now we want to define our x1 as the point of intersection of this line with the x-axis, right? So how to get this x1? Well, if you put x equal to x1 here, then you should get y equal to 0, right? That is the idea. So from here, you can get x1 as x1 equal to a naught minus f of a naught into b naught minus a naught divided by f of b naught minus f of a naught. And this can also be rewritten like this. Now, once you have this, then your initial interval a naught to b naught is divided into 2 parts, a naught to x1 and x1 to b naught, right? Now you will check the sign change of the function f in these 2 intervals. In whichever interval we have the sign change for the function f, we will take that interval and discard the other part of the interval. And then we will take our new interval as the interval in which the function f changes its sign. Now again, once you have that interval, say a1 to b1, you will go to again use the same formula, but now with x2 equal to the same expression, but replace suffix 0 by suffix 1. And this process will continue in a similar way. In general, for every n equal to 0, 1, 2, and so on, we define our xn plus 1 as this expression, which can also be written in this form. Remember, this is the point of intersection of the line joining these 2 points with the x-axis. Now, once you have xn plus 1, now we have to devise the algorithm to shrink our interval. How will we go ahead with that? The rest of the idea is exactly the same as we have done in the bisection method. We will come across one of the following 2 cases. Once we are done n iterations, and when we go to construct the interval for the n plus 1th iteration, we will be computing the value of xn plus 1 using this formula. If that value happens to be a root of your equation f of x equal to 0, then you will stop the iteration there. If it is not so, then what happens? We will have one of these 2 cases. The idea is exactly the same as in the bisection method. And depending on whatever happens, either this happens or this happens, we will have to define our new interval an plus 1 comma bn plus 1 in this way, right? We have explained it in the bisection method. Therefore, I will not explain it here, but I hope the idea is clear here. So this is how we will keep on doing our iterations. Once you have an plus 1 to bn plus 1. With that, you will now go to find xn plus 2, right? Once you have xn plus 2, you will check whether it itself is a root of your equation. If not, again, you will see where the sign change of the function f is happening, whether in the first part of that interval or in the second part of the interval. Depending on the situation, you will define the interval of the next iteration. That is the n plus second iteration interval you will define, and you will keep on going like this. Now the question is, how will you stop the iteration on a computer? Theoretically, we can go on like this. As long as we are not hitting this case, you will generate a sequence of real numbers, theoretically. But when you are doing it on a computer, you need to also worry about the stopping criteria, right? When to stop this iteration process? Well, in the case of bisection method, we had a very natural stopping criteria. That is, we always see the length of the interval. If it shrinks below a pre-assigned positive quantity, then we can comfortably stop the iteration in the bisection method case. Can we follow the same idea in the Regula-Falsi also, is the question. Well, the situation here is not that easy. Why? Because let us take this example, a naught to b naught, and I have the equation f of x equal to 0 in such a way that the graph of the function f is like this, say. Then you can see that the first iteration is like this. The second iteration will be going like this. This is your x1, x2, and now x3 will be like this. And you can see that your sequence xn will be moving in this direction, and it can never cross this and go and touch b naught. Therefore, bn minus an, if you look for this number to be less than epsilon, this can never happen in this case for a sufficiently small epsilon, right? Therefore, a very easy and comfortable stopping criteria which worked very well with bisection method will completely fail in the Regula-Falsi method. Now, how to decide whether we want to stop our iteration at some n or we have to proceed further is the question. Well, let us formally write the idea. If the first case happens, that is at any n, if xn plus 1 coincides with the root of the equation, how will you see? You just substitute xn plus 1 into f and see if it is exactly equal to 0. You have no ambiguity. You will stop the iteration at nth level itself. You will not go to worry about the interval an plus 1 comma bn plus 1, right? If that doesn't happen, and if your sequences keep on going, then on a computer, you have to worry about what stopping criteria you have to adopt to in order to stop the iteration on a computer and decide that the xn plus 1 at that iteration is an approximation to my root. Well, there are some suggestions to use as a stopping criteria. Yes, the length of the interval may not converge to 0 in the Regula-Falsi case, right? I have given you geometrically an example. Now, therefore, the question is how to stop the iteration. Well, one way to stop the iteration is to look for the absolute error, right? At a kth iteration, you got xk, and you can see that xk minus r modulus is less than whatever tolerance that you have. If this happens, then stop the iteration. This is the most convincing and realistic condition that we can use to stop our iteration. But unfortunately, it is practically not possible because primarily we do not know the value of R. That is why we are going for any approximation method, right? If we know R already, then why are we going to an approximation method to compute this X case? We don't need to do that, right? Therefore, this idea, although it is the most convincing and natural way of stopping our iteration, it is practically impossible to use this condition. Then can we have other ideas? Well, one very straightforward idea is you just choose a k arbitrarily, some natural number, and simply stop your iteration after k iterations. That is, say k is equal to 100 you take, and you stop your calculation once you hit k equal to 100. But rather this is blind. Why? Because even though k is very large, there is no guarantee that you are pretty close to your root, right? Or it may happen that the convergence happens, say, in the 5th, 6th iteration itself, then unnecessarily you will be computing the iterations up to k equal to 100. It may look easy for us to implement this idea as a stopping criteria in our computer code, but it is not convincing at all. What could be the next idea for stopping criteria? Well, you can take Cauchy condition for some real number epsilon greater than 0 and integer n given to you. You may take n equal to 1 also. Stop the iteration when xk minus n is less than epsilon. See, this is the Cauchy condition. If you recall from your real analysis course, this can be used. This is one possibility. Or alternatively, you can also use this condition, right? This is something similar to the relative error. Any of these two is perfectly okay to use as a stopping criteria. Another idea is the residual error. That is, you just take mod f of xk. And if that is less than epsilon, you may choose to stop the iteration. This may also look a bit convincing, but this is very dangerous because it may not work always. We have mentioned this in the previous chapter itself. Residual error works very well for linear systems, but not for nonlinear equations. Let us take an example. Your function f may be going very close to x-axis and then take a turn, and then it goes far away and intersects the x-axis. In which case, if you go to check this condition, by any chance, if your x lies in a small neighborhood of this point, you may tend to stop your iteration, but actually your root is very far from that value xk. Therefore, this idea, although again very easy to implement, but not very convincing, and because it may not always work. But this criteria is convincing and also is reliable to use as a stopping criteria. Well, this is all about how to stop an iteration on a computer. Coming to the theoretical question, suppose my iteration is going on infinitely, then the Regula-Falsi method, just like bisection method, will give me a sequence of real numbers, right? Now the question is whether this sequence converge or not. We omit the proof of the Regula-Falsi convergence theorem for this course and continue with an example. Let us take up the same example as we did in the bisection method. This will also help us to compare these two methods, at least in this particular example. Let us take f of x is equal to sin x plus x square minus 1. As a first step, we have to find a closed and bounded interval in which the nonlinear equation has at least one root. As in the bisection method, let us take the initial interval to be 0, 1 And if you recall, the formula for x1 in the Regula-Falsi method is given by a naught f of b naught minus b naught f of a naught divided by f of b naught minus f of a naught, right? Here a naught is 0 and b naught is equal to 1, and you just substitute these values in this expression and get x1 is equal to 0.54304. So let us try to understand this graphically. You can see that f dash of x is equal to cos x plus 2x. And in the interval 0, 1, you can clearly see that this is positive. And similarly, f double dash of x, if you take, it will be minus sine x plus 2. And that is always greater than 0. From these two expressions, you can clearly see that f is strictly convex and monotonically increasing in the interval 0, 1. Let us try to understand this graphically. Let's take the interval 0 to 1, and the graph of the function f will look something like this. This is the root of the equation f of x equal to 0, which we would like to capture. And our x1 is nothing but the line joining the points 0, f of 0 and 1, f of 1, right? And this point is what we were trying to capture. x1, maybe graphically it may not exactly looks like 0.54304, but overall idea is this. Now from here, we have to get the interval for our next iteration, that is the interval a1, b1. For that, you have to find the value of the function f at the point x1, which in this case given by minus 0.18837. And you can also see that f of 0 is negative and f of 1 is positive, right? Therefore, f of x1 into f of 0, both are negative, therefore this is positive, and hence you will discard this interval. On the other hand, you can see that f of x1, which is negative, and f of 1, which is positive, is less than 0. Therefore, sign change of the function f is happening in the second half of this interval. And therefore, we will take this part of the interval for our next iteration. Therefore, you will define x1 as a1 and b0 as b1, which is actually 1. So this is the overall idea of how the iteration will go on. So this is the graphical interpretation of it. In the next iteration, you have to find x2 by using the same formula, but now having a1 and b1, right? Therefore, a1 f of b1 minus b1 f of a1 divided by f of b1 minus f of a1, right? That will be precisely the point of intersection of this line with the x-axis, right? That is, this is the point x2, and that is given by 0.62662 And again, the function value at x2 is negative. And previously, if you remember, we have taken a1 as x1, which was again negative, and f of 1 is positive. So again, you will go to choose your a2 as x2 and b2 as b1, which is actually equal to b0, which we took as 1, right? In that way, you can see that at every step, the interval length will shrink, but it will not tend to 0, right? Because this part is always untouched in the iterations, and therefore, unlike bisection method, in Regula-Falsi method, you generally cannot expect the interval length to shrink to 0, okay? Now, once you get the interval a2, b2 from your iteration 2, you can go to find x3 now with the same formula, and x3 is given by 0.63568. Now, if you recall, we have also computed 3 iterations for the same equation using bisection method, and in that case, we got x3 as approximately equal to 0.625. And here, in Regula-Falsi method, we got the value of x3 as 0.635. If you recall, our exact root is 0.636. You can see that when compared to the bisection method where we got 0.625, you are pretty close to the exact value of the root in the Regula-Falsi method than in the bisection method in this particular example. However, remember, this may not be the case always. There are examples where bisection method goes faster than the Regula-Falsi method. You can easily construct such examples graphically at least. This completes our discussion on closed domain methods.